take a look at the generalized definition of work. Now, if force is constant, we have work is equal to force times displacement. If force is not constant, however, there are a couple ways that we can approach this. Take a look at the segments where the force is constant, or we can look at the segments where the force is close enough to constant, which in theory would be an object that's falling, that is close enough to constant force, as free fall I'm talking about. Or we can look at the average force over displacement. Now, let's take a look at the evolution of that. So if I have a force and a displacement as shown right there, the work, just multiply it straight up. Force is constant over that displacement, we get 12 joules. It's a one-dimensional problem, so we could get away with, instead of using I hat, we could just make that the positive direction and still get the exact same answer. It's a scalar product, so there's no vector in that solution. Let's take a look at it graphically, because this is going to lead towards the more general solution. So looking at this graphically, we have a constant force, so it's a flat line with respect to position, and I just picked two numbers here so that my displacement is equal to 4 meters. If we look at the area of this curve, because that's basically my base is my displacement and my height is force, and I multiply it out and I end up with 12 joules. Not coincidence. So we can generalize that the work is the area under the force times position graph. Now I have under in quotation marks here because that's the language that is used. Let me also throw in, this is the parallel part of the force. Since this is usually a specific direction, this is the part that is parallel to that. If my force is -3 newtons I hat and my displacement is 4 meters I hat, I multiply it out, the fact that they're in opposite directions, or it's a one-dimensional problem, so I can just do -3 times 4, I get -12. Graphically, it would look like this, where my force and position are like this. When you talk about the area under the curve, they're not talking about this section down here as under the curve, because that's my curve right there. Area under the curve is a reference to where the function is and where the horizontal axis is. So this is considered the area under the curve, and it's a negative area because it's -3 times 4. And so just realize that area under the curve, when the curve is beneath the horizontal axis, is a negative area. We now have a segmented one. So for the first 3 meters of displacement in the I hat direction, we have 4 newtons, and then we have 2 newtons after that for the next 5 meters. So a total of 8 meters in the I hat direction. So work 1, so this first segment right here, we're just multiplying 4 times 3, we get 12 joules. Work 2, I have 2 newtons over 5 meters, and that's 10, and so I get 22 joules. My force is not constant for the entire trip. I am able to solve it by looking at each segment separately. Graphically, we're looking at something like this, where my force gets cut in half at the 3 meter mark and then continues on. Now, it doesn't really matter what the initial position is, because I gave you the information. My final for the first segment is 3 meters after whatever my initial position is, and then at the very end of the problem, it's 5 meters more than I was at the 3 meter mark. In other words, 8 meters past what I started with. If I look at the area, if I look at it from this and then this, then it's 4 times, this is 4 times 3, and this is 2 times 5. Or I could look at it from this, and I get this, and then this little segment right here, and we end up with 22 joules still. Get the exact same answer. Doesn't really matter how you find the area, just as long as you do it correctly. We're going to throw in a change. My force is not constant anymore, but I do have it as directly proportional to position. This should be a straight line right there. This is not part of the problem because I go from 2 meters to 7 meters, so anything that's outside of the problem I'm going to ignore. So looking at it from the area point of view, area is, I break it into a triangle and a rectangle. My triangle, area is 1/2 base times height. My base is 5. My height is from 6 to 21. So my area is 1/2 base times my height, and then plus the area of this rectangle, which is just base times height. Or as I wrote here, height times base. Ended up with 67.5 joules. Now, because force and position are directly proportional, I could find the average just by averaging the initial and final values. Again, this works if they're directly proportional, or I should say if the plot is a straight line from the beginning to the end. And so my average is just the average of 6 and 21, or 13.5 newtons in the I hat direction. So the work is average force times displacement, which is 13.5 newtons times 5 meters. They're in the same direction, just multiply it out to get the same answer. Or with calculus, and if you don't care about the calculus, just get through this part, and I introduce some other terms later on. This is not the last part of this presentation. And so work is, or integral of force dot dx. My change in position and my force are in the same direction, so I can just, the dot product can go away and just multiply them straight up. There's my force times my change in x, and so I end up with 67.5 joules again. Now let's take a look at if it varies with x as a curve. And finding the average is, you can't really find the average of something that curves like that particularly easily, and so you'll probably end up using calculus. Now, in order to solve something like this, you would treat it as a series of rectangles, and so I just started out with just a simple, I treated a rectangle right there where the right side edge is at the curve, right side edge is at the curve, and I can come up with a crude estimate for the area under the curve. Ultimately, I want just that area right there. I wouldn't design a building based upon something like this, but it gives me at least a ballpark. Now I can get a better estimate if I break it up into more rectangles, so the right side of each rectangle is at the right-hand side. And so if I make my rectangle smaller, which increases the number of rectangles, then I end up with a better estimate. So let's take it to the extreme. So my width becomes infinitesimally small, not zero. Very important that. And we ultimately end up with an infinite number of infinitesimally small rectangles. That is the area of the rectangle. And when you get to the integral, we're down dealing with an infinite sum. And so this is the branch into calculus. What Calc 2 does when you get into integration, or derivatives, as I believe it's initially called, when you get into Calc 2, that is the steps that you go through, and you eventually show that as these triangles get smaller and smaller, you do approach a specific value, which is the area. And also, for those of you who are wondering, why not take a lower estimate here, take the left-hand side and the big one, and yeah, that will get you a better estimate than overestimating or underestimating. However, ultimately, calculus is used. And so just a quick example, I have 3 newtons per square meter, x squared minus 2 newtons in the I hat direction from 4 meters to 7 meters, and we just integrate from 4 to 7, and we end up with 273 joules. And the last example is if I start out with the same I hat component, but I have a j hat component this time, and I'm going from this position to this position. Well, I deal with the I hat part and deal with the j hat part. So the I hat part, I'm going from 1 meter to 4 meters, so from 1 to 4 of 3x squared minus 2 dx. And then in the y side, I go from -2 to -6, as demonstrated, or as written out here, and we end up with, well, due to the antiderivative or the integral of this, and x cubed minus 2x from 1 to 4, and 8y from -2 to -6, and ultimately you end up with 25 joules. And those are some basic problems. Obviously, this is not quite as basic, but it gives you a bigger picture, I hope.